Today's lesson is going to be building up on what we discussed in the previous session, which was all to do with different types of errors and how do we identify them and how do we correct them. In order to do that, we need to have a planned approach, and that planned approach is in the form of a test plan or a testing strategy. So today we're going to be looking at the methods of testing available to us and selecting appropriate type of data for a given method. How do we go about that? We're also going to be looking through walkthroughs, white box testing, black box testing, integration, alpha, beta, acceptance, and stub testing. Now, all of these types of tests are normally a part of a test plan, but we're also going to be looking at where do you do this testing? Where does it fit in the development cycle? Do you just do it in the testing phase, or do you do it through each particular phase? And that's going to be the crux of this particular session. So let's start by looking at some of the key terms that we're going to be using in this session. So do pause the video and jot these down in your exercise book. We start with test strategy, which is an overview of the testing required to meet the requirements specified in the analysis stage. This is what the program should do, and if it doesn't do that, the program is not really a success. We're going to be looking at a test plan. How do we design it? What the details that are needed to be part of a test plan. We're going to be looking at a walkthrough, which is a formal version of a trace table or a dry run. You look at predefined test cases and you check for that. We're going to go through different types of test data. Most of this is covered at IGCSE level, but if you're not sure, this will be a nice review for that: normal, abnormal, extreme, and boundary. And then we're going to look at the specific forms of testing: white box, where you test every logical part of the program, every procedure, or black box testing, where you just look at the inputs and outputs, whether the program is doing what's it supposed to be doing, and so forth. We're going to be looking at integration testing, especially if you're working in a team and people are developing different modules. You combine them and you test them out together. Or sometimes, you finish programming a module and the other ones aren't done, so you use some kind of dummy data. And that's the purpose of stub testing. So we're going to be looking at that: alpha testing and beta testing, internal testing, external testing, and then finally acceptance testing. So do pause the video, go back through both sets of key terms, and make sure you jot these down in your exercise book. So let's start by looking at program testing. Now, testing actually begins from the moment we start writing or thinking about these tests. However, what most people do is they never document it. Often you'll probably notice that you go straight into programming code and you just start writing it. So test strategy is needed often in the analysis stage, where you decide the requirements of the program, what the user wants, and a strategy shows an overview of what testing might be required to meet those requirements. Because obviously if you don't meet them, the program is not a success in the eyes of the user, and often you don't end up getting paid for it. So this strategy shows how and when the program is to be tested, and normally a test plan is part of that, where you show all the stages of testing and every test that might be performed on the application. And these results of these tests can then be added to the plan at a later stage to show whether it's been successful or it led to some kind of code change. Now, apart from the testing stage in the development lifecycle, testing occurs at every stage. In design, you probably are going to do something like dry running to check that your algorithms are working. During the development of the program, you might be focusing on syntax errors and trying to fix those, and logic errors. And then you might be doing testing to fix runtime errors later on. And you might also be trying to work out whether the requirements are being met. So during the design stage, you often write pseudocode, and that's where a dry run, where you as the developer works through the program module to module and manually work out that the logic is correct and it's working as it's intended to. But this needs to be documented, and we document this in the form of a trace table, and you should have a lot of experience of trace tables from IGCSE as well. So let's start by looking at how comfortable you are with trace tables, and do you have a basic pseudocode testing task on screen. So I've created a procedure. It has a few issues with it. Go through that, and you can use the test data which is on the screen. So pause the video Use the headings for the columns number 1, number 2, sign, answer, and output. The test data is used to dry run the algorithm, then highlight the possible errors that occur once you've gone through that particular algorithm, and how could you use the results of the dry run to fix the errors. What would you do to fix it? Now, you might be able to spot the error straight away, but what I want you to do is go through the process of using a dry run to detect it and show evidence for it and then fix it. Okay, so pause the video and go through this. Hopefully you got something like this as your answer. And you probably spotted this pretty quickly that when it's doing the subtraction function, it's actually adding and not subtracting. And obviously there is a division by zero error that can also occur, which can lead to an error. And for that, we will need to do some fixes. Now do share your answers with me, and I will check those. But if you want to check these right now, think about how you could change the calculation. And the second one is, can we put in some kind of validation or exceptions to address the division by zero error? And of course, if you picked out the biggest error, that the procedure is never called, so the program wouldn't run, that would be awesome as well. Now, a walkthrough is basically a formalized version of a dry run, and that normally uses predefined test cases. So think about this. You were kind of doing a walkthrough of my particular algorithm. So another member of the team independently dry runs the pseudocode, and then you check and spot my errors, because sometimes it's very difficult to spot your own mistakes. Now, during the program development and testing, each module is tested as set out in the test plan. So in our case, we might have a test that says to test the positive calculation, and another one to say to test the negative calculation. And the purpose is to ensure that it works as expected. Now we could use different types of test data. So we could say, well, we're going to use normal data, which is 20 and 10 and then plus, and then abnormal data where we're just going to have strings. So we expect 30 for the answer to the normal data, and for the abnormal data, the expectation is that there would be an error message. Now when you run the actual test, you write the actual outcome, and you quite clearly, when you run my pseudocode, you will get 30, and you'll get an error message if you type in a string, because there is no validation present at the moment. Now, if we were testing the negative calculation, which we hope works as expected, the normal data is 20, 10, and minus, we expect the answer to be 10. And the abnormal, we expect an error message because we're entering strings again. But when we actually run this particular pseudocode and we dry run it, the actual outcome is that because of the mistake in the operator, we end up with 30. So that's where we go back and try to fix the pseudocode. Now this leads us nicely into normal test data, which you saw, which is accepted by the program, and then you have abnormal test data, which should be rejected by the program because it's unsuitable and could cause problems. However, there are two more types. One is extreme test data, that is on the limit of what's accepted, and you know this from IGCSE, where if you had a percentage, 0 and 100 would probably be the extreme examples of test data. Now boundary test data is like extreme, but you also include a value that is on the incorrect side. So -1 and 0 would be one set of boundary test data where -1 is not acceptable, but 0 is acceptable because the student can get 0. And the other set would be 100, which is acceptable because somebody can get perfect marks, but 101, you can't get 101% out of 100, so that's rejected. So boundary test data always comes up in pairs. So what are the other types of testing out there? Well, you can check whether your procedure works as intended, and for that we use something called white box testing, where someone goes through the procedure and says, well, is everything working? Is the logic correct? Is every part of the program, all the if statements, all the loops working as they should? Black box testing, on the other hand, tests modules, inputs and outputs. It doesn't actually care how you got there. You might have the most inefficient program, but if you type the right input and get the right output, it passes black box testing, because sometimes you only are concentrating on the end results. Now, integration testing is testing all the different types of modules. Think back to when we talked about rapid application development cycles, where you might have multiple teams working on different modules at the same time. So when they finish these modules, these have to be put together into one program and checked to see that are they working as they're intended to. And then you have stub testing, that sometimes you might end up with modules of code which are completed and the others are still being programmed. So you might just end up using dummy modules for testing purposes, just to make sure that the module or the procedure that you've coded works as intended. So stub testing just focuses on individual parts, and it uses dummy modules for testing purposes, just to make sure, okay, that would be the output from this module. Let's use that in the main program and see what's going on. So now you've finished off your program. So the modules have been tested. You've got your integration testing going on. Stub testing was done. Everything works, hopefully. And at that point in time, you're going to go into alpha testing mode. And in this one, the completed or nearly completed program is tested in-house by the development team. So you check everything, the program as a whole. Now, hopefully you found some bugs and you corrected them. The next stage is beta testing, and that's when you go outside and get a small group of users before the release of the software, and then you check it in the real world. How are actual users going to interact with it? And hopefully that finds some errors and bugs, and then you correct those as well. And once everything is done, you go into acceptance testing, where the completed program is given to the actual client, and they check the requirements and they sign off the acceptance that, okay, it works as it should. Now, often what happens is that you've done everything, the program works, it's accepted, you got paid the amount that you were supposed to, and everyone's happy. But over time, there's a software update in the operating system, a hardware change, maybe the user that you wrote the program for, their requirements have changed. That might lead to some kind of program maintenance. Now, programs themselves do not wear out, but they might not work in unforeseen circumstances. Logic or runtime errors that require correction may occur from time to time, or the users sometimes themselves might want the program to work in a different way. So we end up with that program maintenance challenge. So in this case, we end up with three different types. First is corrective maintenance, which is to do with fixing any errors that might have occurred. And you trap a runtime error that might have been missed in testing. You know countless examples of software which might have bugs, especially games. And then there's normally a patch or something released to fix it. Then you can have something called perfective maintenance, which is used to improve the performance of a program during its use. Maybe you spend time doing your black box testing instead of your white box one, and then your program works really, does what it's supposed to, but it's not the most efficient program. And then you go about improving the speed of response of that particular program by writing efficient code. And then there is adaptive maintenance, which is used to alter a program so it can perform any new tasks that are required by the customer. For example, they might want it to work with a new piece of hardware they've acquired, or a company's software systems have changed, or in the case of a company takeover, a new company has acquired them and they have a different set of systems, so they want their existing program or software to be compatible with them. All of that can come into play, and that's where adaptive maintenance comes into the picture. Okay, so by now you should know what the purpose of a test plan is and what we mean by things like walkthroughs and dry runs. You should also know the difference between white and black box testing, how integration and stub testing are different from each other, what's the difference between alpha, beta, and acceptance testing, and you should also be able to explain the three different types of program maintenance: corrective, adaptive, and perfective. Now, after this particular review, there are a couple of questions for you to try out. So please do try those out and share your answers with me. These are past exam paper questions related to the software development cycle and testing in particular. So do go through them and get back to me if you have any further questions. This is the end of this particular unit, software development, and we're going to move on to ethics and copyright next. Okay, this particular question is pretty straightforward. So go back to your structure diagrams and use the information in A and B to populate and complete a diagram. This question is in multiple parts. So first you will need to think of data structures, then look at the pseudocode, and then do a dry run through that particular pseudocode, and finally describe what the algorithm is actually going to do. And this can be done by simply reviewing the pseudocode and looking at the results of the trace table.